Hi everyone, I'm Shanjun. It's my great honor to be here and introduce our recent work. This work was done with my brilliant co-authors and supervisors. Okay, let's start from the title. We can see that there are three key points. Firstly, we mainly focused on the challenges of tabular biomedical data. And secondly, to address these challenges, we propose a novel feature selection method. And thirdly, it's called ProtoGate. Today, I will present ProtoGate from four aspects. To begin with, we will look at some preliminaries to understand ProtoGate. As mentioned before, we mainly focus on the tabular biomedical data. So for this dataset, one major characteristic is the high dimensional and low sample size feature. Specifically, the number of features is generally way more bigger than the number of samples. According to the cursive dimensionality, it's very hard for machine learning models to achieve high accuracy on this kind of dataset. And secondly, these datasets are generally heterogeneous across samples. In other words, the important features can vary from sample to sample. Therefore, an intuitive solution is to perform local feature selection. In other words, we select important features on an instance-wise basis. This sounds conceptually attractive and ideal, right? But actually, we found there are still many limitations in existing methods. Here we further detail the hypothesized reasons for these limitations. Firstly, let's look at the two paradigms here. They summarize most of the pipelines in existing local feature selection methods. The first one is called joint in-model selection. Here, an trainable local selector will select some features from the original sample, and then the predictor will make predictions based on the selected features. This sounds intuitive and straightforward. However, because both of them are trainable, they can co-adapt with each other and cheat the users. Specifically, they can achieve high accuracy with low fidelity feature selection. Here we show an example. When we apply an existing local feature selection method for digit classification on the MNIST dataset, we found that it can achieve over 95% accuracy. This is really high. However, for each figure, it only selects one feature, and this feature is not really informative. If we give people such feature, people cannot tell this is 0, this is 1, which means that the model has high accuracy, good, but the used evidence, in other words, the features, are just noise for humans. So this is low fidelity feature selection, which is unacceptable for real world applications. To address this problem, some researchers further propose the second paradigm. In other words, we first train a predictor and then we freeze it. And then we use another feature selector to explain the predictions by providing feature importance. This is also straightforward because now the two components are decoupled. Of course, there's no more co-adaptation. However, it also loses the in-model explainability of selected features. In other words, our predictions are now made based on all the features, but the selected features are never really used for predictions. They're just used for interpretation. So that's also a harm to the interpretability of the model. Therefore, we propose the third paradigm, which is called disjoint in-model selection. It can not only preserve the advantages of the two existing pipelines, it can also provide interpretable explanations and human understandable predictions for the final decisions. We will detail this in the next section on model design. Okay, here we show an architecture overview of the proposed ProtoGate. First, we input a sample, and then we perform two-stage feature selection. Firstly, we select the globally important features, and then we refine them to locally important features. And this is done by outputting a mask. This mask can mask some of the features by setting values to 0, and then we multiply the mask with the sample, and this is feature selection process. After this, we input the selected features or the masked sample into the predictor for final predictions. This is basically the prototype-based prediction. In other words, we use the majority class of the nearest prototypes at the final predictions, and the nearest prototypes are used as prototypical explanations. Therefore, the two-stage all have their own distinct advantages to the existing methods. Firstly, in the global to local feature selection, we are one of the first to highlight the globally important features. And in the prediction stage, firstly, we know that the prototype-based prediction aligns with the clustering assumption, and the clustering assumption requires ProtoGate to select features that cluster samples of the same class together, and this is coherent with the characteristics associated with biomedical data. And beside this, our predictor is non-parametric. This is really cool because now the predictor is not trainable. In other words, it cannot co-adapt with the feature selector anymore, and therefore we can preserve the fidelity of selected features, and the co-adaptation problem is mitigated. And last but not least, the predictions here, now we accompany it with some prototypical explanations. And the explanations are similar to how humans make decisions. Like when doctors diagnose patients, they provide the most similar cases they have encountered before. So they're quite human-friendly and interpretable. Here we further provide two illustrative examples of ProtoGate inference process. Firstly, on the left side, we show the interaction between the global selection and local selection. On the right side, we further detail how to interpret the predictions made by ProtoGate from the perspective of prototypical explanations. Next, we detail how we evaluate the effectiveness of ProtoGate. Firstly, on the real-world datasets, we evaluate 4 aspects of ProtoGate, including accuracy, this is classification accuracy, and also the feature selection sparsity, speed, and model size. So in the first figure, we want the model to have high accuracy as well as fewer features selected. For instance, if we are given 5,000 features and we select 4,000 for accurate predictions, accuracy is good, but 4,000 features is still too hard for humans to understand. It's still a heavy burden for the practitioners. Therefore, we want the models to select as fewer features as possible. So we can see that ProtoGate has the highest overall accuracy and also it selects the fewest features compared to prior studies. In the second figure, we can see that ProtoGate is faster, and in the third figure, ProtoGate generally requires less space for training and inference. This is really cool because they show that ProtoGate has high applicability for real-world biomedical tasks. And furthermore, on the synthetic dataset, we further evaluate the co-adaptation problem avoidance. Specifically, we compare the prediction accuracy and the fidelity of feature selection. Generally, ProtoGate strikes a good balance between them, which show that this method can predict the fidelity of feature selection well while achieving very high accuracy. Okay, these are basically the core contributions and main results of our work. If you're interested, please feel free to refer to our paper and code. And also, if you have any other questions regarding the paper or regarding the tabular biomedical data, anything you want to discuss, please feel free to email me. I'm happy to take them and discuss anything interesting with you. Thank you very much. See you in Vienna.